Hello, everyone. Welcome to Unit 2. It is time to define the derivative. After completing your lesson preview, you should have figured out that the secant line as related to the average rate of change is really important, but often what we're looking for is an instantaneous rate of change. So the slope at one point in time. That is the derivative. The limit problems that we practiced in Unit 1 are the basis for most of the definitions in calculus. Specifically, today we're going to use our limit problems to define the derivative. Now, the derivative comes from the slope of your secant line. When we represent the slope of the secant line, or the average rate of change, we generally write f at b minus f at a over our b minus a. If our goal is to determine the slope at one specific point, let's say c, we're going to rewrite our problem such that we have b equals c plus some small amount delta x. We're also going to let a equal that value of c. Rewriting the slope of the secant line gives us f at our c plus delta x minus f at c, all divided by, now think about b minus a, it is now delta x. If we were next to let that delta x get as small as possible, heading towards 0, that actually gives us the slope of our tangent line. So the slope of the tangent line is the limit as your delta x heads to 0 for f of c plus delta x minus f at c, all divided by your delta x. Now we know that the slope of the tangent line is also where the instantaneous rate of change occurs. An instantaneous rate of change is the derivative. So the instantaneous rate of change is the slope of your tangent line, but you know the slope of the tangent line is truly your derivative. Saying slope of the tangent line is a bit awkward at times, so the notation we're going to use is f prime of x. So the limit definition for your derivative comes in various forms. F prime of x can equal the limit as delta x goes to 0, f of x plus delta x minus f of x over your delta x. Another form of the derivative, you might see the limit as your b goes to a of f of b minus f at a divided by b minus a. And a third way that you might see your derivative is the limit as h goes to 0, f of x plus h minus f of x divided by h. So back to the notation. F prime of x is an excellent way to ask for the derivative, but often you will see f prime at some sort of number 4. Now when you see f prime of 4, what this means is find f prime of x, then you're going to substitute in the 4 as your x value. Another definition, if you let y equal f of x, this is not a definition, this is your notation, you might see that dy dx is equal to the derivative, and dy dx is the derivative of y with respect to x. Lastly, if you see dy dx at x equals negative 2, this tells you once again, find your derivative, then substitute in x equals negative 2. All right, so now you know the definition of the derivative. It is the slope of the tangent line or the instantaneous rate of change at a particular point. So now that we know the definition of the derivative and a little bit of the notation, it's time to actually determine a derivative. So f prime of x equals, let's write the limit notation several times as we practice so that I know you understand the notation. We have the limit as delta x goes to 0, f of x plus delta x minus f of x divided by your delta x. When we do our substitution, we're going to rewrite the problem. Always keep that limit notation until you've actually substituted in the 0. We end up with the quantity x plus delta x squared plus 2. Don't forget that little plus 2. Minus the quantity x squared plus 2. All divided by your delta x. Now, once you've completed that substitution, it's time to do your algebra, just like you practiced in your limit unit. We're going to multiply x squared plus 2x delta x plus your delta x quantity squared plus 2, distributing the negative, all divided by delta x. You're being very careful with the notation. Notation matters. So as you can see, your x squareds conveniently cancel out. The 2's are gone. And you may have done enough practice to know that the next piece that's going to cancel out will be your delta x's. So you have 2x delta x plus a delta x squared, all divided by delta x, which simplifies. Once again, I've not gotten rid of my notation, keeping my delta x. I have 2x plus delta x once I cancel out a delta x from each of these terms. At this point, we're ready to substitute, and the limit as delta x goes to 0 is 2x. That's it, guys. You found your first derivative. The derivative is the slope of the function, but it's supposed to be at a particular point. The next question changes the problem, looking for average rate of change. So average rate of change brings me back to the slope of the secant line. And the slope of the secant line is f at 10 minus f at 6 over 10 minus 6. So we can combine some of the questions that we were working on before to complete these problems. And we get 102 minus 38 over 4, which reduces to 16. So the slope of the secant line is 16. Oh, look at question C. So question C, once again, is a derivative problem at 7. So this is saying find the slope of the tangent line specifically when x equals 7. That's what f prime of x means. It's looking for the slope of the tangent line. But we know that f prime at x is equal to 2x. So then f prime at 7 becomes a substitution problem. 2 times 7 is going to be 14. So the slope of our tangent line at 7 is 14. Now we want to find the equation of the tangent line at x equals, I'm also going to find it at 7. I'm not sure. Mine got cut off. So if I determine the equation of the tangent line at x equals 7, then we know that the slope of our tangent line is 14. We know that x equals 7, but I need the y value. So y is going to come from f of 7, which equals 7 squared plus 2, or 51. So I have y minus y1 equals m times x minus x1, which leaves us with y minus 51 is your 14 times x minus 7. It is not necessary to solve for the y, but I do suggest that you know your point slope formula for writing the equation of a tangent line. If you didn't know it before, put it in the list of things that you need to know. All right, so the next set of problems, we're looking at graphs in order to answer questions. Question A, what is the approximate value of the slope of the secant line? So we know that the slope of our secant line can be represented by f at -1 minus f at -3 over our -1 minus -3. So the denominator, as you can see, is going to be 2. But the numerator, we're going to have to do a little bit more work. So let's go back. Looking at the numerator, f at negative 1. So we go left 1. And, looks like we're going up 2.5. So 2.5 minus f at negative 3. Well, where's negative 3? Right here. And then looks like negative 1, 2, 3. Negative 3 is 0. That's convenient. So we have 2.5 divided by 2. And that is going to be a nice 1.25. Next question, we're going to approximate the value of the slope of the tangent line. So it might be helpful if you draw the tangent line to x equals negative 3. So when we draw that tangent line, let's draw it in. Now I want to find the slope of that tangent line. I can't really use the value at negative 3. So I'm going to pick 2 points that are nice points on this curve. It looks like this. And if you use a straight edge, you're going to do a much better job than what I did. So the slope of our tangent line, or if you want to write it as f prime at negative 3, looks like it might be up 1, 2, 3, 4, 5, 6, 7, 8, and over 1, 2, 3, 4. Now, you might have a slightly different answer, but use the answer that is how far up and over you are going with this problem. In my case, I think it's 2. So wait, the next problem says approximate f at negative 3. The answer should be 2 because it's the same answer for the slope of your tangent line. So for question D, we're to determine where f prime of x is equal to 0. So f prime of x is equal to 0 means that you have a horizontal tangent line. If I draw in where horizontal tangent lines occur, looks to me like we might have a horizontal tangent line at 2, but also right about here, you can estimate that to be f at negative 1.3. So f prime at negative 1.3 is equal to 0, as well as f prime at 2 equals 0. So when you equal 0, that's where you have a horizontal tangent line. And now the numerical derivative. So you're given data. We're looking for the derivative at 2. Now, when we find the derivative at 2 using the data, we want to choose a point that's one to the right and one to the left of our x value. So I want f at 2.1 minus f at 1.9 divided by 2.1 minus 1.9. Now, it might bother you that we're going to the right and left, but that is how you find a numerical derivative. So in this case, we're going to have 1.1025 minus 0.9025 over 2.1 minus 1.9, and that is approximately equal to 1. Next, if we're looking for f prime at 3.6, we are going to approximate again since this is numerical data. So 3.6 is this time on the right-hand side, and I don't have data to the left, do I? So this one, we're going to say, does not exist because you have to have some data to the left and some data to the right in order to determine it. If you were to figure out what is f prime at 3.5, that one you could do, and it will end up to be approximately negative 9.75. However, f at 3.6 does not exist. There is an alternative form of the derivative, which we did not put in our original list, and it is the formula written right here. So for example 4, this is also a numerical derivative. The reason it's called numerical is because you're told specifically what your delta x is. And to solve such a problem, you're going to do substitution again. So for our substitution, we're going to determine f at 2.001 minus f at 2 divided by your delta x, which is 0.01, and that's going to be approximately equal to the derivative at 2. Once you substitute, just take those values, put them in for f of x, so at 3 to the 2.001, minus your 2 to the 0.001 divided by your 0.001. Substitute this into your calculator, end up with approximately 9.893. And one more time, this is the approximate slope of the tangent line at specifically x equals 2. For our next example, we're going to find an analytical derivative for f of x equals 4 over the square root of x. So using our definition, we know that the limit as delta x goes to 0 of f of x plus delta x minus f of x is going to give us a derivative if we divide by delta x. Substitute into our function f of x. Make certain that as you substitute, you keep your limit notation. We're going to have 4 over the square root of your x plus delta x minus the function itself, which is 4 over square root x, all divided by your delta x. Now, of course, we're going to need to find a common denominator, which leaves us with the limit as delta x goes to 0. 4 root x minus 4 times the square root of x plus delta x. In your denominator, you're going to write your delta x, the common denominator, x plus delta x, and your square root of x. And now we multiply by our conjugate, and that conjugate, of course, is going to be 4 root x plus your 4 root x plus delta x. And the denominator will have the same expressions, so that we're really multiplying by the factor of 1. Okay, keeping your limit notation. Once again, this is equal to the limit as your delta x goes to 0. Squaring our first term, and then we square that second term. Look how nice this gets rid of our square root, and we're left with an x plus delta x in the denominator. Now, we should actually just have 16x. There we go. Fix that little problem. All divided by. Now, the denominator is quite complex. We have our delta x, square root of x plus delta x, another square root of x, and look at this, 4 root x plus 4 root x plus delta x. Okay, that's lovely. So what happens when you distribute your negative? Our 16x's cancel out. Ooh, the numerator now has negative 16 delta x, and your denominator still has a delta x, so this is working beautifully. 16 delta x over the delta x's cancel. Keep all your square roots, write carefully, write neatly. You don't want to miss any little detail as you work through this problem. Plus 4 root x plus delta x. Nice. Okay, our delta x's cancel, as we said. We're going to substitute, let delta x go to 0. Let's do that. And what are we left with? The numerator is now negative 16. And your denominator is going to be the square root of x times the square root of x times the quantity 4 root x plus 4 root x. And put that 4 in here. We have 4 root x. There we go. Simplify some more. Look at what happens, guys. We have negative 16 in the numerator, x in your denominator, and we have an 8 root x. Simplify, because you really should make this look as nice as possible. Negative 2x to the 3/2 power. All right, now remember, what did we just find? We found the derivative. The second part of our problem is specifically asking you to find the slope of the graph at the points 1, 1 and 4, 2. So if we're looking for the slope of that graph, we're looking for f prime at 1. Substitute the 1 into the problem, you end up with a negative 2. Substitute your 4, so f prime at 4, and we end up with negative 2 over 4 to the 3/2. And as a reminder, take the square root of 4 first, get your 2, and then 2 to the third is going to be 8. So simplify, you get 1 over 4 as your derivative for that problem. Last part, is it possible to find the slope at 0, 0? So if I were to take my 0, 0, substitute it in, f prime at 0, it looks to me like you're trying to divide by 0. Are we allowed to divide by 0? No. Not only that, if you take a look at the original problem, is f at 0 actually equal to 0? And now you have your lesson practice. So for the next 20 minutes, I want you to try the questions 1 and 2. When you look at questions 3 and 4, you should be just fine. Use your definitions. Number 5 has a typo, so skip it. Then you will practice until you get to question number 9. Turn off this video now, practice the problems, and we will discuss some of the answers once you've completed your practice. All right, so after you did all the work for number 1, did you notice that the slope that you came up with is 1.5, which kind of makes sense since you're finding the slope of a linear line. So the slope of a linear line, line that's linear, is going to be just the slope that you see. Now for number 2, you probably had to do a little bit of estimating in order to figure out the slope of the graph through the points x1 and x2, but estimating is just fine. So for question number 3, make certain your substitution is accurate and that you multiplied your cubic out correctly. Now for number 4, take a look at the differences between the slopes of the secant line and your derivative. What you're going to find is that your derivative was steeper and therefore must be greater than the slope of that average rate of change. So for questions 61 and 62, make certain you take a good look at your graphs. Check to see what the derivative looks like as compared to your original function. Question 63 and 64, using the alternative form of your derivative. Another way to do the problem would have been f at 2.1 minus f at 1.9 divided by your 2.1 minus 1.9. You'll get a more accurate answer. So this is probably the way that would be best for doing questions numbers 63 and 64. As you probably figured out, question 8 has a variety of answers. So I might want you to start with the instantaneous rate of change. Build these in before you do the average rate of change. Then your graph should come together. Using technology is a valid way to find your derivative. Make certain, though, when you do your practice problems that the directions have a picture of a calculator by it. If not, you should not be using a calculator. So as you practice number 9, following your directions, you should have ended up with g prime at 2 was equal to negative 0.083. You may have had trouble with g prime at 15 if you did not change your window to keep g at 15 within the window. So you needed to change your x values to go from the minimum, perhaps you chose 0, maybe you chose your x max to equal 15, or excuse me, to equal 20. Then it doesn't matter what your y values are, but your x values had to be between 0 and 20 in order to encompass the 15. Once you do that, you should be just fine with finding your derivative. Now, to write the equation of the line, you can use technology for that, or you can use your y minus your y1 equals your m times x minus x1. When you do, you should end up with y equals negative 0.083 plus 2.025. So make certain you know how to use technology in order to find that derivative. All right, we're at that point where it is time to think about homework. So your lesson follow-up is on page 103. And one more time, just so you remember, you are not to work more than 60 minutes. So lesson 60 minutes complete some of these problems, if you're having a lot of trouble, make certain that you get a hold of me to get some help. Have a great day.